Right, welcome to an Introduction to Quantum Mechanics by Griffiths and Schroeder. We will start right away. I do not want to waste any more time, and I will go straight into 1.1 of, aka the Introduction to the Schrodinger equation. So, before we dive into quantum mechanics, it's pretty useful for us to get an analog of its relation to classical mechanics. So let us start by analyzing a classical system. So start with classical. And in my classical system, let's say that I have a particle in one dimension. And let's constrain it to x hat. And let's say that my particle is located somewhere and it's defined by x of t. And let us exert some force F on my particle. So the entire purpose of classical mechanics can ultimately be boiled down to trying to find the position, x of t, the velocity, v of t, and the acceleration, a of t, of my particle. And from this, we can derive more complex values, such as the energy of the particle, the momentum of the particle, and various other things. However, fundamentally, classical mechanics ultimately boils down to trying to find these three values for any given system. And the way we actually solve for these systems is we use Newton's second law, force equals mass times acceleration. And the quantum mechanical equivalent is kind of the same thing. Just like how in classical systems we are trying to find parameters such as position, velocity, and acceleration through the use of a fundamental equation, which is Newton's second law. In quantum mechanics, we are doing the same thing. We are trying to find parameters given an equation that we already have. So in quantum mechanics, my analog to my three parameters, position, velocity, and acceleration, is a quantity known as the wave function psi. And what psi actually is, I will describe in the later section, but for now, let's just consider it as this mystery quantity that is the quantum mechanical analog of these three values. And the way that psi is actually solved for is using a formula known as the Schrodinger equation. So the Schrodinger equation is expressed in the following way. An imaginary number I times h bar, which is the reduced Planck constant, times the partial of our wave function psi with respect to time, is equivalent to negative h bar squared divided by 2 times the mass of the particle, multiplied by the partial, the second partial derivative of psi, this time in terms of x squared, plus the potential energy of our system multiplied by psi again. So psi, just from this, we can tell that psi is in terms of position x and also in terms of t. And this so-called mystery quantity is the crux of our goal of analyzing any sort of quantum system. Any problem can ultimately be boiled down to trying to find the value of psi given some initial condition in our system. Now, I hope that just from looking at this equation, you're concluding that this is obviously a very complicated thing. This is by no means a simple equation like force equals mass times acceleration is. And indeed, in many times, it actually is impossible to solve for the Schrodinger equation in terms of psi. This book will give a number of very specific situations where we actually can, in fact, solve for psi. However, in most realistic systems, we actually can't. And quantum mechanics, in the very end, is ultimately a field, just like any other physics field, where you approximate certain things in order to make life easier for yourself.